Hi, and welcome to this webinar. Today I'm going to talk about the Graviton2-based instances, and we will see how you can benefit from them when running your workloads on Amazon EC2. I'm Arthur Petitpierre. I'm a AWS Specialist Solutions Architect, focusing more specifically on those Graviton2-based instances. As you probably know, AWS has one of the broadest and deepest compute platform choice. We offer many different instance categories, and those instances have many different capabilities. Whether it is the choice of processor, the amount of memory you have per instances, or the type of storage you want to have with them. Overall, we have more than 350 different instance types. AWS started its cloud journey with Intel processors. We later added AMD EPYC processors on Amazon EC2 instances. And finally, in 2018, we announced the first generation of instances with a processor that has been designed internally at AWS, the Graviton processor. The Graviton processors have been designed with the 64-bit Arm architecture, leveraging the Neoverse cores, and they are targeted specifically for cloud-native workloads. The first generation of instances supporting those Graviton processors was the Amazon EC2 A1 instance. It provided customers with an optimized cost and was bringing pretty good performance for scale-out application. Those instances are available in 6 different types with up to 16 VCPU, and they're available today in 9 different regions. The A1 instances was a pretty interesting customer success. We had many different customers who adopted them, and they were the first instances to bring the ARM64 architecture as a first-class citizen on EC2. We then received some feedback from those customers asking us to be able to broaden the scope of ARM64-based instances to many different types of workload. And in 2019 at reInvent, we introduced the Graviton2-based instances. 3 different families, M6G, R6G, and C6g instances. Those instances feature the Graviton2 CPU, and that second generation is definitely a leap forward compared to the previous one. It's still based on the 64-bit Arm Neoverse architecture, but it now offers 30 billion transistors compared to the 5 billion of the first generation. It's built using a more modern manufacturing technology on 7 nanometer instead of 16 with the first generation. And overall, it brings 7 times more performance. It has 4 times the number of cores of the first generation. It has now 64 cores and a faster memory. Today, AWS offers Graviton2-based instances in 4 different families. The first one is the M6G, which is a general-purpose instance with a good balance of amount of memory and number of VCPUs. We offer the T4g family, which is the first burstable family of instances using an ARM64-based processor on AWS. And for the T4g, we have a free trial. We offer the C6g family that is more targeted at compute-intensive workload. And finally, we have the R6g, which is a memory-intensive instance. They are all available now, and they do have variants using local NVMe-based storage. That's all the instances with a final D, like M6GD, C6GD, and R6GD. They all come in different sizes, from 1 VCPU to 64 VCPU, and they even come as a metal instance, which is a specific instance type where we removed the virtualization layer so that you can get direct access to the underlying hardware. If we look into the details, you can see here the different characteristics of the M6G instances. You can see that they offer 4 GB of memory per VCPU, up to 64 VCPU per instance, and up to 25 gigabits of network bandwidth per instance. The C6G is pretty similar. It offers 2 GB of memory per VCPU instead of 1, and otherwise it comes in pretty much the same sizes, up to 64 VCPU. It also has a metal version, and it also offers 25 gigabits of network bandwidth. The R6G is yet another variant with 8 gigabytes of memory per VCPU and up to 512 gigabytes of memory. It also comes in sizes from 1 to 64 VCPU and in a metal version. The variants with internal NVMe-based SSDs are displayed on that slide. They're available for all the different families, M6G, R6G, and C6G, and offer different amount of disk capacity depending on the instance size. The T4g is available in 7 different sizes, from 2 VCPU up to 8, and from alpha gigabyte of memory up to 42. The Graviton2-based instances have been built leveraging our Nitro platform. So it uses the Graviton2 processors. It uses the Nitro security chip, which is an AWS custom designed chip that is integrated on the motherboard and protects the hardware resources from being tampered by any malicious code that would run on the instances. So, for example, it protects the firmware on the system by providing a cryptographically protected API that prevents attackers from tampering the firmwares. It uses the Nitro cards, which are cards that are connected to the PCI Express bus of the instances and emulating hardware component on the PCI Express bus, like the EBS disks or the network cards. And finally, it leverages the Nitro hypervisor, which is the AWS developed hypervisor, a pretty lightweight hypervisor that acts as a thin layer between the instances and the underlying hardware. Overall, all the Graviton2-based instances are priced with a 20% lower cost compared to the same size in the x86 family. They offer up to 40% better price performance compared to x86 instances, and today they offer the best price performance within their family on AWS. AWS also starts to offer managed services based on the Graviton2 processors. We've just announced ElastiCache using the Graviton2-based instances. And with this new generation, you can get up to 45% better price performance using those instances. We have also announced a preview for Amazon RDS on M6G and R6G instances, and Amazon FSx for Lustre, which is our managed version of the Lustre file system, now supports AWS Graviton2-based instances. In terms of software, the Graviton2-based instances are supported under Linux and a couple other open source based operating systems. All the major Linux distributions are running perfectly well on the Graviton 2-based instances. We definitely recommend Amazon Linux too, for which we took great care to optimize the performance and ensure that you would get the best experience. But you can also use Ubuntu, and particularly the latest version, which provides support for the large-scale extension of the latest ARM64 generation. You can also use SUSE or Red Hat starting from the 8.2 version. In the containers landscape, Docker supports the ARM architecture since a long time already. We also support the Graviton 2-based instances with Amazon ECS and also with Amazon EKS, both being our container orchestration managed services. We support multi-arch containers in our ECR service, which is the Amazon version of a container registry. And when I say that we do support multi-arch, it means that under the same name, you can store an image that would have an x86 version and an ARM64 version. Firecracker, which is the Amazon version of micro VM, supports the ARM64 architecture. And Bottle Rocket, which is an open source operating system targeted at running containers, does support the ARM64 architecture too. As far as the tools and softwares are concerned, on AWS, obviously, most of the tools provided by AWS do support the ARM architecture. I'm thinking there of the different agents like Amazon CloudWatch or Amazon Inspector. And if you are running Java-based workloads, Amazon Corretto, which is the long-term supported Amazon released version of OpenJDK, is obviously supported and optimized on the Graviton 2-based instances. The Graviton-based instances are supported by many software vendors. In the CI/CD landscape, for example, Jenkins, GitLab, or Drone.io are supporting the Graviton-based instances. In the security landscape, software like CrowdStrike are supported on Graviton 2-based instances. And if you are looking for a framework to monitor your application, the Datadog framework is supported on Graviton 2-based instances. Now, let's do a deep dive on the Graviton 2 processor. So the Graviton 2 processor is the latest generation released by AWS on the Graviton architecture. The first version was the first ARM processor on AWS. We made it a first-class citizen on EC2, but it was a first attempt and a pretty modest chip. The Graviton 2 processor, on the contrary, is a way different beast. It features 4 times more VCPUs, up to 64, twice the performance per VCPU compared to the first generation, and it's built using a modern manufacturing technology. It's in 7 nanometer. And overall, it's a way bigger chip, 30 billion transistors instead of 5 billion with the first generation. That processor has been built using the Arm Neoverse N1 cores, and it's ARMv 8.2 compliant. And actually, AWS worked closely with Arm on the creation of the N1 cores. We brought to the table our experience running large-scale workloads in the cloud and on everything that customers are looking for when selecting a processor in the cloud. So it features a pretty large level 1 cache with 64 kilobytes of L1 cache and 1 megabyte of level 2 cache per vCPU. We ensured that it has a low overhead when handling interrupts, which is something super important on a server. It also has all the primitives that are needed to very efficiently implement virtualization and context switching on a server. You have hundreds of processes running at the same time, so it's super important to be very fast when you are switching context. It has all the features that you can expect from a modern CPU, like dual SIMD unit, and even data types to accelerate ML inference, like int8 or FP16. One important difference between the Graviton2-based instances and our other Intel or AMD-based instances is that on the Graviton2-based instances, every VCPU is a physical core. We don't do multi-threading on the Graviton2 processor, which protect us from a couple specific attacks, cache-related attacks, and also helps that processor scaling very well at high VCPU counts. In terms of interconnect, the 64 cores are connected together with a mesh that offers 2 terabytes per second of bisection bandwidth. It has a pretty large last level cache with 32 megabytes of last level cache. And in terms of topology, it offers a flat topology. From any core on that processor, you see the same path to the memory and the same path to the other cores. For an application developer, it means that you don't have to pay attention to where you are allocating the memory. On our Intel-based instances, for example, if you're using the full size, like a C5 18XL, the underlying system is made of 2 different sockets. So if you're allocating the memory on one socket and trying to access that memory from a process running on a core on the other socket, you're going to pay a penalty in terms of bandwidth and in terms of latency, because you have to go through the interconnect between the two sockets. On the Graviton2-based instances, on the contrary, we have a single socket with the 64 cores, so you can allocate the memory anywhere. You will see the same performance regardless of from which core you're accessing it. Now let's have a look at the level of performance that you can expect from the Graviton2 processors. A classical benchmark that is run each time a new processor is released is the SPEC CPU benchmark. It's an industry standard benchmark, CPU intensive. And in this case, we've been running it on all the vCPU concurrently, so loading the system entirely. And we are comparing the performance on a per vCPU basis. The comparison here is done between an M6G and an M5. And when we look at the results, we can see that the M6G, for the integer part of the benchmark, is 44% faster than an M5. And for the floating point version of the benchmark, we are up to 24% faster on the M6G. Now let's have a look at a workload that would be closer to a real application. Here we've been measuring the performance in a load balancing setup using the NGINX web server. Here it is configured as a proxy, and so we have on the left a load generator that is sending requests through the NGINX proxy, and the NGINX proxy is load balancing the requests on a pool of web servers. And when we are running that workload, we observe that on the M6G instances, we are up to 24% faster in terms of numbers of requests per second compared to an M5. Now, if we are to run benchmarks using Memcached with a pretty similar setup, a set of load generators on the left, and then the system under test running Memcached, and when doing that comparison between M6G-based instances and M5, we observed that we are 43% faster on the M6G compared to M5. In terms of latency, we are also better under load on M6G compared to M5 with a better 99% percentile latency. If we measure video encoding on M6G instances using the X264 application, which is an open source application that you can use to encode and decode the H264 format. When comparing M6G to M5, we observed a 26% better performance on the M6G compared to the M5. In terms of feedback from our customers, so we've run a pretty long preview program, and then those instances are now available since May for the M6G instances. So we've collected a lot of feedback from customers. And one that I really love is the feedback from the folks at honeycomb.io. Lise Fong-Jones, who's one of their principal developer advocates, have worked on the migration of their application from Intel-based instances, C5 in this case, to Graviton2-based instances. They're running an architecture with a set of Go-based workload running in containers. And when they shifted their workload from C5 to M6G, the performance was so much better on the M6G that they realized that they could use 35% fewer instances on the M6G instances. And that quote is from the time when C6G was not yet available, but now they have replaced the M6G by C6G instances, still using 35% fewer instances than with C5. So they're accumulating instances that are 20% cheaper, and they're using 45% less instances compared to their previous setup. To run the migration of this application, it took them an elapsed duration of 15 days. And during these 2 weeks, they actually spent somewhere around 15 hours actually working on migrating the application. Another interesting review is the review conducted by AnandTech. Those guys have run an extensive set of benchmarks comparing AWS Intel-based and AMD-based instances. And when running those benchmarks, they observed that the Graviton2-based instances were overall significantly faster and cheaper than any other instances in the AWS portfolio. We also received customer feedback for different types of workload. Here you can see a couple of feedback regarding Java-based workload, for example, from Mobius Space. Those guys are running a Java-based backend service. And switching to M6G, they got a 30% performance improvement compared to their previous setup using M5 instances. Now let's talk about what it means to transition a workload to Graviton2-based instances. So if we look at the language level, any application that would be written in an interpreted or byte compiled language, something high level like either Python or Java or Ruby, those kind of applications can usually run on Graviton2-based instances without any modification. There are a couple corner cases, like the fact that some of the Python modules are actually written in lower level languages like C or C++. So those might have to be recompiled. For Java, you might have extensions using GNI modules that might be written in C or C++, and obviously also those ones would have to be recompiled. But most of the time it would typically just work. And even when you have to recompile some of those modules, they're usually pretty portable. Even languages like .NET Core are supported on Linux and run perfectly well with a pretty good level of performance on the ARM64 architecture. When it comes to application written in lower level languages like C or C++ or Go or Rust, of course, they have to be recompiled for the ARM64 architecture. You can't use the binaries that have been compiled for the x86 architecture. But every major compiler supports the ARM64 architecture. And if the application was written in a portable way, there's no reason it would not compile pretty well and run on ARM64. In some cases, you might find applications that are leveraging either intrinsics or that are embedding some handwritten assembly. Of course, those part of the application would have to be rewritten specifically for the ARM64 architecture. In terms of the AMIs that you might use on the Graviton2-based instances, as we previously said, most of the major Linux distributions do have support for Graviton2-based instances, so it's just a matter of picking the ARM64 version of those AMIs. Of course, we recommend to use recent enough version of those distributions to enjoy the best level of performance on the Graviton2-based instances. When it comes to AWS tools and SDKs, all our SDKs are fully supported on the Graviton2-based instances, even the ones for the low-level languages like C or C++. When it comes to the ARM64 architecture and the different container services, Amazon ECS and Amazon EKS, which are our container orchestration environment, are both supported on Graviton2-based instances, and you can mix x86 and ARM-based instances in a cluster. Amazon ECR supports multi-architecture manifest lists, so you can build containers for both architecture and store them under the same tag. And AWS Code Build allows you to build application on ARM64-based instances, so you can use it to build container or application for both Graviton and Graviton2-based instances. Docker itself provides a tool to build containers in a multi-arch environment. You can use BuildX to do that. And when it comes to migrating an application, the way we recommend to conduct such a migration is to first start by identifying all the dependencies. The dependencies at the application level, but also all the dependencies that your workload might have in your production environment. So not only the libraries or the runtime of your application, but also anything that you need to run your application in production, like the monitoring tools or the logging tools or the security-related daemons or agent that might be useful for you in production. Those dependencies might be open source or proprietary. There's now a pretty good coverage from the open source ecosystem on the ARM64 architecture. And if you have any proprietary piece of software for which you're lacking ARM64 support, please let us know. We are deeply involved with the software vendor to help them getting their application ported and available on Graviton2-based instances. So don't hesitate to either reach to your AWS account team or to send us an email. and we will get in touch with the software vendors and provide them with the needed level of support, or we will give them access to Graviton2-based instances so they can get their application ported. The second stage of a migration project or process is to test the application. And we definitely recommend that you would test your application on the new architecture. There's a certain number of bugs that might emerge when running on a new architecture. And so running the usual range of unit testing, acceptance testing, and pre-prod testing is super important when you adopt the Graviton2-based instances. As far as your infrastructure as code is concerned, you will have to update it to take into consideration the Graviton2-based instances. That might be when using tools like CloudFormation or AWS CDK. And usually the changes are going to be pretty minimal. It's going to be mostly modifying the instance type, modifying the AMI ID, or potentially some of the user data to reflect the newly added Graviton2-based instances. And then once you have tested the application and updated your infrastructure as code, we recommend to gradually migrate your production workload to Graviton2-based instances. You can do that using, for example, a blue-green deployment method, and gradually move the workload to Graviton2-based instances while monitoring at the same time and checking that everything is going well. If you want to go further, AWS has and keeps on updating a getting started guide for the Graviton-based instances. It has been assembled by a mix of solutions architect and services team from AWS, and it is designed to help you transitioning your applications. There are tips and tricks about, for example, which flags you should use with the different compilers when recompiling an application for the Graviton2-based instances. And it gives information on what are the best supported version of either applications or operating system. We update it regularly based on the feedback we received from customers, and also based on the changes in the application ecosystem, be it on the open source side or on the proprietary side. Overall, the Amazon EC2 M6g, C6g, R6g, and T4g instances that are all powered by AWS Graviton2 processors provide you with up to 40% better price performance compared to their x86-based instances, the comparable ones I mean. They can support a pretty broad spectrum of workloads, from application servers to databases or in-memory caches. And most of the Linux distribution and the open source framework are supported on those instances. Finally, all of them are available also with local NVMe disks for your IO-intensive applications. Now let's have a look at a quick demo. During this demo, we will deploy the simplest possible web application. It's gonna simply take a request and send back the architecture on which it is running to its user. On the left, we have a load balancer, and the load balancer is going to send a request to either an x86 instance or a Graviton-based instance. So let's switch to the console, and we will start by creating a repository on ECR to host our container images. So let's get started. I'm gonna call my registry hello. That will be perfect to host a hello container. And I will create the repository. You can explore some details about the repository, and here you can see that no image obviously has been stored yet to that repository. So now let's switch to an instance that I've already started, running Ubuntu 18.04 on an x86 host. Here we can see that we are running on an x86 instance. I have prepared my application, and if we switch to the hello app folder, here I have two files. One is the Go code for my application. So it's a very simple code. We have a main function that is starting a web server on port 8080. And when it gets a request, it will simply transfer the request to a small handler that is going to send back the architecture of the system on which it is running. To build that, I've written a Docker file that you can see here. We are going to use a multi-stage building environment. First, we will pull a container with the Golang environment, build our Go application, and then push that to a minimalistic container so that we will run that in a very minimal environment. So I'm gonna get our account ID and export that in the environment, as we will use it later. And now I'm gonna authenticate our environment with some temporary credentials so that we can connect to our ECR repository. So now we are authenticated. The next step is that I'm gonna build a x86 version of my application. So let's do it. Now it's done. Let's put a tag on it, and then we will push that one with the tag lov1 to our repository. Here we are. We will go back to the console, and on the console we will use CloudFormation to deploy our application. So let's create a stack, a new one, and for that we'll use a first version of our application stack that I'm gonna deploy here. Let's give a name to that stack. Here as the parameter we have the ability to select the AMI on which it's going to be running. The version of the container is going to be v1. I will select my key pair, select all the subnet in my environment and my VPC ID, and we will deploy it. We are almost there, and now we can create the stack. The stack creation is in progress, and we will wait until it has deployed all our resources. And among the resources, there will be a load balancer. Those addresses will appear in the Outputs tab. If we switch back to the event, we can see that our x86 instance is being deployed. That's the first version of the demo. And in a second iteration, we will redeploy that same stack with this time both an x86 and an ARM64 instance. Okay, so our load balancer is now ready. Let's try to connect to our application. And here we are. Our application is telling it that it's running on a AMD 64 instance. Okay, let's now change a little bit the application so that we will rebuild it to be multi-arch. So the first thing we are going to do here is we'll start by installing Docker buildx. So we will build that first. Okay, now let's create a folder to put our plugin for buildx. That's perfect. We will now pull a container with emulation capability. So let's start it. Okay, we got it. And we also need to modify the Docker configuration so that it would be able to use its experimental features. Here we are. Okay, so now we are ready to use buildx, and we will use it to create an environment that would build containers for both our x86 architecture and the ARM architecture. So let's create that new builder. We'll call it dual builder. The next step is to tell buildx to use it and to bootstrap it. Okay, so we are done with the bootstrapping, and we can see that we have the ability to build for x86, but also ARM64 and a couple of others. So we are still in the folder where our application and our Docker definition reside. So we are going to be able to build it again, but this time targeting two different architecture. So let's now launch the build for a second version of the container. I'm calling it V2 here, and we will build it for both the ARM64 version and the x86 version. Let's do it. Application is now built, and we will go back to the CloudFormation console to update our stack. So let's go back to the stack, and we will update it. We will replace the current template by a new one. So we will select the V2 here and click Next. Our parameters are going to be the same. We will just change the path to the second container. We will use the V2 here instead of the V1. And let's deploy it. So what that one is going to do is that it's going to deploy a new version of our stack that will contain two different instances. The x86 instance that we had in the first place, and an additional ARM64 instance. So same as the previous step, we will now have to wait for our two instances to be deployed, and once it's going to be the case, they will be added to the Elastic Load Balancer, and we will be able to connect to the application and test the result. So let's wait for the update to finalize, and once it's going to be done, we will go back to the ALB. Okay, so now our ALB is ready, and we will be able to test the application. So we will copy the DNS name of our ALB and switch back to our environment where I have prepared a test environment. So it's a simple Python script that is taking the address of the ALB as an argument and launching several requests against it. So let's execute it. Let's run. So the first instance answering is an ARM64 instance, And now we have an AMD 64 instance, and we can observe that some of the requests are served by our ARM64 container and some others from the AMD 64 container. As a conclusion, during this demo, you have seen how to create a repository with ECR, how to build a multi-arch image using BuildX and how to store it in ECR, how to deploy an application with CloudFormation, and overall as how easy it is to transition from x86 to ARM64. While transitioning that small application, we have left the code as it was. There was no modification needed, despite the fact that the application was written in Go and need to be recompiled for each of the environment. And now we will switch to the Q&A part of that webinar.